Welcome to this session of pharmacokinetics. Today I will extend my discussion regarding is extravascular administration by one compartment. Previous video I have discussed about the general derivation of how I derive the general equation for extravascular, that is equals to kfx naught by Vd into k minus ke to the power minus ket minus of e to the power minus kat. In the previous discussion video, I have also explained how to derive a UC and also how to derive total clearance. Today's discussion will mainly deal with the method of deriving the Cmax and the Tmax values. You know that extravascular route of administration is characterized by the presence of maximum drug concentration and the time required to achieve that. This is a very important and characteristic pharmacokinetic parameter that helps to enable the bioavailability condition of the drug in the systemic circulation. It also helps to understand the extent of therapy or toxicity that can be achieved by the drug in the systemic circulation. It is also a very important component to be considered during in vitro in vivo correlation, that is IVIVC. Well, so today's discussion will be how to derive the Cmax and the Tmax values. So let me start off with the derivation of Tmax first, then I will go for Cmax. So for deriving equation for Tmax, I will consider this equation first. Into e to the power minus ket minus of e to the power minus ka. Multiply that. If we multiply that, we get it as kaf x naught by Vd into Ka minus Ke e to the power minus Ket minus of Kaf x naught by Vd into Ka minus Ke e to the power minus Kat. This is the equation we are getting. Now differentiating both the sides with respect to time, we get dC by dt. So here differentiating this e to the power ax if you consider. So due to this differentiation, this constant will come at front. So here my constant is minus ke, so it will come at the front. So it will become minus ke into kaf x naught by Vd into Ka minus Ke minus of, so same thing. So here what is happening? Minus k multiplied by minus k minus, so you can say it is becoming plus k square f x naught by Vd into Ka minus Ke. Sorry, e to the power, it will be minus Ket, it will be e to the power minus Ka. Considering a condition when I am achieving the Cmax, the dC by dt, that is the rate process, turns out to be 0. Why? Because the rate of absorption and elimination becomes equal to each other. So my dC dt value will be 0. If my dC dt value is 0, so if I bring this thing to this side and I keep it on the right hand side, this part, so it becomes Ke into Kaf x naught e to the power minus Ket divided by Vd into Ka minus Ke equals to K square f x naught e to the power minus Kat divided by Vd into Ka minus Ke. So we are getting the value as like this. So we can remove this parts. So your K and square is getting cancelled. F x naught is getting cancelled. So we just, what I do it over here, very simple thing. I'm just bringing K by K in this form. So K is over this side and e to the power minus Ke over this side. And this is Ke is over this side, e to the power minus Ket is on this side. So what I am doing, I am just bringing the factor as Ka by Ke. So you are making like this. So it will become e to the power minus Ket by e to the power minus Kat. It is becoming like this. Very simple. You go for taking ln. Okay, go for taking ln. So you know that ln e to the power something by ln e to the power some this by this. So same as log. So log of a by b equals to log a minus log b. So same way ln of a by b equals to ln a minus ln b. So this is, if I consider ln e to the power minus Kt minus of ln e to the power minus Kt. Okay. So what I can say, this base is e to the power base something. So this becomes 1. So minus Ket will come outside. So we can write it as minus Ket plus Kat. Okay. So if I convert to log, what happens? Into 2.303 equals to this one. So instead of that, I am just making it as t as a common. So Ka minus Ke into t divided by 2.303. Okay. Now I have done one thing that I didn't say, that from here where I am considering this equals to 0, I have to consider this as a Tmax. Okay. So this all is nothing but your Tmax when dc by dt equals to 0. So this is your Tmax. Okay. So this is your Tmax. So Tmax now can be written as 2.303 divided by Ka minus Ke. It will go up, it will go down, into log of Ka by Ke. So this is how you are determining the value of Tmax. So Tmax equals to this one. So I can write down Tmax, what I derived, 2.303 divided by Ka minus Ke log of Ka by Ke. So this is what I am getting. So hope so you understood what we are doing over here. Okay. Now if you say so our next discussion video will be on Tmax. I am separating so that you don't have a problem of confusing of yourself. So this is a video which is based on a derivation of Tmax. Hope so you understood how I did it. The basic thing we have to remember here, in the step we have a process where I am considering my red process, that is dc by dt equals to 0 when t equals to t max. This is the consideration I am making of over here. So when I am making this becoming 0, this value is coming on the left hand side, and then I am just removing the common factors. We are getting this value. So this is the important factor which we have to remember. Okay, and this is also very essential as far as your derivation for this we are going to use for the derivation of C max. So you have to remember this, and thereafter the derivation, and we get the value of T max. You look at one thing which is very important to find, that the value of the T max, what will be the value of the T max, mainly depends upon two primary rate factors. Two primary rate factors. They are absorption rate constant and elimination rate constant. You can see there is no other factor involved over here. There are only two factors, absorption rate and elimination rate. That means the rate at which it will go inside and the rate at which it is coming out will determine the maximum, the time by which I can achieve the maximum drug concentration. Hope so you understood this concept, and thank you.